Whenever we make measurements in a laboratory or elsewhere, we will have uncertainty in those measurements. And that is a limitation of the equipment, or if it goes even down far enough, you could reach the uncertainty principle. So there will always be some level of uncertainty when we're measuring something in the lab. Now, that's perhaps okay, but one of the things that we should do is identify how much uncertainty we have in a particular result. And what is it? Well, ultimately, it's a range of values for a measurement or result. So, for example, if we chose a Class A volumetric flask that is 100 milliliters, the standard uncertainty for it to qualify for Class A is to have it plus or minus 0.08 milliliters. And that is to say, without calibration, this flask is supposed to contain somewhere between 99.92 milliliters minus 0.08, 100 minus 0.08, or up to 100.08, which is just the plus version of that. Now, this is an example of absolute uncertainty. So we would just take the value and either add or subtract to get our range of values that our true value would be contained in. Now, it's possible to lower the amount of uncertainty in a measurement or some object like this by first calibrating our equipment. And we could calibrate this equipment by measuring the volume of water or whatever the solution is in a different method other than by volume, other than by using this flask. The standard way to do that is to weigh the flask before, so a dry flask, put it on a scale, weigh it, fill it to the mark, weigh the flask again, and then use the density of water and whatever else we need to calculate what was actually contained in that flask. And if we do that, we'll often get a better result than this standard Class A, just simply by calibrating it. All right, well, anyway, absolute uncertainty, that is expressed in the same units, and you could just add and subtract to get the range. There's another kind of uncertainty that is useful, and that is relative uncertainty. And quite simply, we take the absolute uncertainty, which is our 0.08 milliliters in this example, and divide by the magnitude of our measurement, which in this case would be 100. So we'd take 0.08, divide by 100, and then that would be our relative uncertainty. Now, often relative uncertainties are expressed as a percentage, so then we would multiply by 100. So in this case, it would be 0.08%. But I like to leave things, when I'm doing calculations using relative uncertainty, still in a non-percentage form, just because then I'm not multiplying by 100 and dividing by 100 all the time, and that can lead to confusion or just add extra steps that are unnecessary. So now that we have uncertainty down, we should talk about what happens when we have more than one measurement involved in an analysis or coming up with a value. And to do that, we will have to propagate the uncertainty. Because if we make a measurement and then we use that measurement in a calculation in conjunction with some other measurement, which is common, often we're not just using one piece of equipment one time. Perhaps we're using a pipette and we're also using a volumetric flask, and we may be using a balance and a burette. Who knows? There's a lot of different equipment. How do we take the uncertainty in each one of those measurements and add them together, or propagate the uncertainty through? Now, you may be thinking that we could simply take all of the low values, add those together, all of the high values, add those together, and then we'd get a new range, which would be quite a bit larger. But that would ignore the fact that not every measurement, or not every thing that we do in the lab will be in the same direction. Because hopefully we've eliminated our determinant errors. Those are errors in the same direction. And we're only left with undeterminate errors, which could be in a positive or negative direction, and it has a very random chance in either way. So if that's the case, then some of the errors may cancel each other out. And so we don't actually just add the errors together. Instead, we propagate the error. So in the next video, I'll talk about how to propagate the error using addition and subtraction operations. Then after that, we'll include multiplication and division. And finally, we'll do a video that combines different operations, so an addition subtraction step and a multiplication division step. There are other error propagation formulas out there for logarithms and exponents and other things like that, but addition, subtraction, and multiplication and division are what analytical chemists encounter the most, and so that's why I wanted to make a video on those particular ones. They're also relatively easy to remember formulas.